Hello and welcome back to my channel. Today I'm making a video on the online qualification rounds of Hashcode 2021. Again, I'm dividing this video into parts. In the first part, I'm going to explain the problem statement. Then we are going to look at how I solved it on the day of the online qualification rounds. Finally, I'm going to try and optimize my solution. Before I start, I want to thank you guys all so much for the support that my last video got. It seems to have helped some of you, and I appreciate all of the support and you guys subscribing and watching my other videos. There are so many of you now, so thank you. I really appreciate your support, and because I have a full-time job, I will try my best to make a video a month. If you have any suggestions, please leave them in the comments. Part 1. The problem statement. Traffic signaling. So this is this year's online qualification round problem. Traffic signaling. It took me and my team a full hour to just understand this problem, so don't worry if you need to read it multiple times. There are parts that are vital in this document and parts that are just fun facts. I encourage you to read the whole thing at first and then go over parts that need extra clarification. Introduction. The world's first traffic light dates back to 1886. It was installed in London to control traffic for horse-drawn vehicles. Today, traffic lights can be found at street intersections in almost every city in the world, making it safer for vehicles to go through them. Traffic lights have at least two states and use one color, usually red, to signal stop and another, usually green, to signal that cars can proceed through. The very first traffic lights were manually controlled. Nowadays they are automatic, meaning that they have to be carefully designed and timed in order to optimize the overall travel time for all the participants in traffic. Task. Given the description of a city plan and planned paths for all cars in the city, optimize the schedule of traffic lights to minimize the total amount of time spent in traffic and help as many cars as possible to reach their destination before a given deadline. Problem description. It talks about many parts. This part talks about each section of this problem statement. It includes city plan, traffic lights, cars, after that we get to the input and the output. So let's continue reading. City plan. The city plan consists of one-way streets and intersections. Each street is identified by a unique name. So each street has a name, leads from one intersection to another, does not contain any intersections in between. If two streets need to cross outside an intersection, a bridge or tunnel is used. Each street has a fixed amount of time it takes a car to get from the beginning of the street to the end, called L. If it takes L seconds to drive through a street and a car enters it at time t, it will arrive at the end of the street precisely at t plus L, independently of how many cars are on the street. The example I gave my team was, if it takes me half an hour to drive from home to work and I leave at 8:30, that means I get to work at 9 because I already know how long it takes me to get there. Let's look at this figure. It says a city plan with 4 intersections, 0, 1, 2, and 3, and 7 streets, A to G. Intersections 0 and 2 are directly connected both ways through A street and B street. A street and B street. C uses a bridge over A and B street and does not intersect with those two streets. This is the bridge. Note that while the streets are one-way, it is possible to have two one-way streets connecting two intersections in opposite directions. The example is, intersection 0 and 2 with streets A and B. However, there will never be two streets connecting two intersections in the same direction. So it says it doesn't make sense to have two streets that go in the same direction with an intersection. Each intersection has a unique integer ID. The example we saw was 0, 1, 2, 3. And it has at least one street that comes into it and at least one street that is coming out of it. The next element is traffic lights. There is a traffic light at the end of every street, just before the intersection. Each traffic light has two states. A green light indicates that the cars from that street can cross the intersection and head towards any other street, while a red light indicates that the cars from that street need to stop. At most, one traffic light will be green at each intersection at any given time. While the light is green for an incoming street, only cars from this street will be allowed to enter the intersection and move to any outgoing street. All other cars have to wait. This explanation is quite obvious if you know what a traffic light is, but the fact that they put it out here, just as a reminder, is quite nice. Queuing up. When the light at the end of a street is red, arriving cars queue up, waiting for the light to turn green. When the light is green, one car can cross the intersection every second. One car, 1 second. Keep that in mind. This means that if a green light for a given street lasts for ti seconds, then only the first ti cars from that street will continue their travel. Others will need to wait for the following green light. What this is saying is, if a traffic light is green for 30 seconds, according to this, 30 cars will pass. If there are 50 cars, so 20 cars should remain. Let's look at this graph. Consider an intersection with two incoming streets. A street with 3 waiting cars and B street with 2 waiting cars, and 2 outgoing streets, C street and D street. There are 2 traffic lights, one at the end of A street with T1, 2 seconds, and one at the end of B street with T2, 3 seconds. Picture A. Initially, the traffic light of A street is green and the first yellow car starts moving. Picture B. At T equals 1 second, the next green car from A street starts moving. Picture C. At T equals 2 seconds, A street has a red light and the last red car waiting there needs to stop. At the same time, the traffic light of B street turns green and the first purple car queued there starts moving. Picture D and E. At T equals 3 seconds and 4 seconds, the 2 purple and blue cars that were initially on B street have already passed the traffic light and continued their path. Picture F. At T equals 5 seconds, the light at A street turns back to green and the red car that was waiting there can now move. Schedule. For each intersection, we can set a traffic light schedule. The traffic light schedule determines the order and duration of green light for the incoming streets of the intersection and repeats itself until the end of the simulation. Again, it's saying that traffic lights have a schedule and it loops itself. Let's say a traffic light has a schedule of 4 minutes. Each traffic light is green for a minute and then that loops every 4 minutes. The schedule is a list of pairs, incoming street and duration. Each street can appear at most once in the schedule. The schedule can ignore some of the incoming streets. Those will never get a green light. This is the same idea as the pizzas, where one team could not get any pizza and that was okay. So if one street is not included in the traffic light schedule, that means we've ignored it. The traffic light schedule is controlled by your submissions. You don't have to specify the schedule of all traffic lights. By default, all lights on all intersections are red, yes, cars stuck there will have to wait until the end of simulation. Let's look at this example traffic light schedule. In the following example, an intersection has 3 streets leading to it. A, B, and C all lead to the D street. So we have 3 going to the intersection and 1 coming out of the intersection, which is D street. We consider 3 different example schedules for these traffic lights. It says no traffic light schedule, default. So in the program, if you don't do anything, it means all the traffic lights are red and no car gets to go. Figure 4. If no traffic light schedule is set for an intersection, all of the traffic lights remain red throughout the simulation. Any cars that are scheduled to pass through A, B, or C will be blocked and not reach their destination. Figure 4b. In this example, the traffic light schedule covers only one incoming street, the B street. In this case, B street always has a green light. Any cars coming from B street will always go through the intersection directly, while any cars scheduled to pass through either A street or C street will be blocked and not reach their destination. And here it says, schedule that only covers one street. Finally, the schedule that covers all of the streets. Figure 4c. In this example, the traffic light schedule covers all incoming streets, C, then A, then B. For each street, we can define a different TI, meaning different duration during which that traffic light remains green. I was telling my team that if the duration was 1 minute, this could be green for 20 seconds, this one for 20 seconds, and this one for 20 seconds, and then would loop through again, 1 minute each time. We have read through the traffic light element, and now, cars. Each car is described by the path, a sequence of streets it is going to drive through. The paths are defined by the input datasets and can't be altered. In the input datasets, we guarantee that each car can go through a single intersection at most once. Initially, all cars start at the end of the first street in their path, waiting for the green light, in case the traffic light is red, or ready to move if it's green. If 2 cars start at the end of the same street, the car listed first in the input file goes first. Each car then follows a given path while obeying the traffic lights and needs to reach the end of the last street in that path. Cars are queued up at the end of each street. The first car in the queue can cross the intersection immediately after the light turns green. There is no delay while a car passes through an intersection. Cars after that cross the intersection one after another, 1 car every second. When a car enters the last street of its path, it completes its drive until the end of the street and then is immediately removed from it. This means that the car does not queue up at the end of the last street of its path and does not enter the intersection at the end of it. And this means that when you reach your destination, that doesn't mean you have to continue driving. Let's look at figure 3. This figure shows the state of 3 cars at exactly t seconds, with the simulation starting at t equals 0 and ending at t equals 5 seconds. Meaning we have 5 seconds. The street has L equals 3 seconds, so it takes 3 seconds to cross the street. And it's saying, meaning that any car needs 3 seconds to go from its beginning to the end. The light turns green on the left intersection at the first second and turns red again 2 seconds later. The cars are queuing up at the end of the street, with yellow being the first one. At t equals 1 second, the first yellow car immediately starts moving and reaches the end of the street 3 seconds later, which is t equals 4 seconds. The second red car has to wait 1 second before it starts moving and arrives at the end of the street 3 seconds later, which is t equals 5 seconds. The third purple car did not have enough time to enter the street as the light already turned red. Note that this figure only shows 2 streets for simplicity, When a traffic light is shown to be red, this means that another one in the same intersection has turned green. We have finally reached the input data sets. We can see what the file looks like that we're going to be reading. We understand all the elements, I think. This is the same as the last time where it says how many characters there are and stuff like that. So let's read it. File format. Each input data set is provided in a plain text file. The file contains only ASCII characters with lines ending with a single end-of-line character, also called Unix-style line endings. When multiple numbers are given in one line, they are separated by a single space between each two numbers. The first line contains 5 numbers. This is the input example. Let's look at this and read what the input file is. An integer called d is the duration of the simulation in seconds, or how much time you have. An integer I, the number of intersections, the ID is from 0 to I minus 1. An integer s is the number of streets, v is the number of cars, f is bonus points for each car that reaches its destination before the time ends. This was line 1. The next number of lines contain descriptions of streets. Each line contains 3 things. 2 integers b and e. b is bigger than 0, less than I, e is the same. They are the intersections at the start and end of the street, respectively. The street name, it's a string between 3 and 30 lowercase letters. An integer, L, which is bigger than 1, less than D, is the time that it takes a car to get from the beginning to the end of that street. The next number of lines describe the path of each car. Each line contains 2 things. First one is an integer p, the number of streets that the car wants to travel, followed by p names of streets. The car starts at the end of the first street, meaning it waits for the green light to move to the next street, and follows the path until the end of the last street. The path of a car is always valid, i.e., the streets will be connected by intersections. So this simulation lasts for 6 seconds. There are 4 intersections, 5 streets, 2 cars, and a car scores 1,000 points for reaching the destination on time. The street Rue de Londres starts at intersection 2, ends at intersection 0, and it takes L equals 1 second to go from the beginning to end. So it takes a car 1 second to cross this. The other street, called Amsterdam, starts at 0, ends at intersection 1, and it also takes 1 second. The other one, called Athens, starts at 3, ends at 1, and also takes 1 second. The Rome one, down here, starts at 2, ends at 3. This one takes 2 seconds. Finally, the Moscow one starts at intersection 1, ends at intersection 2, and this one takes 3 seconds to go from intersection 1 to intersection 2. The other lines say that the first car, that's currently stopping at the end of Londres, has a path that is from Londres to Amsterdam through Moscow, and then it reaches Rome. And when it reaches Rome, it doesn't have to do anything else. There is no waiting at the next intersection. The next line says how many streets this car has to go through. It's 3, right? From Athens to Moscow and then Londres. So this was the input file. Let's look at what we should do to submit a file and then get points. It says the first line must contain a single integer, and that's the number of intersections for which you specify the schedule. Our job is to have schedules for intersections. Then, the submission file must describe the intersection schedule in any order. Each schedule must be described by multiple lines. The first line is a single integer, and that's the ID of the intersection. The second one is also a single integer, and that's the number of incoming streets of that intersection covered by the schedule. If we look at this one, it had to cross this intersection, and reach here. So this one has to pass 2 intersections. A number of lines describing the order and duration of green lights. Each of those lines must contain these values. The street name, an integer t, for how long each of the streets will have a green light. Each intersection can only be listed once in the submission file, and each street name can only be listed once per schedule. If an intersection configuration is not present in the submission file, then all of its traffic lights are always red. So this was the input file, and this is the output file of this input file. It says that there are 3 intersections with traffic light schedules. On intersection 1, the traffic lights are green for 2 different incoming streets. For the Athens one, for 2 seconds, for Amsterdam for 1 second, then again Athens. And then the other one is intersection 0, is green for 1 street only, and that's the laundress one, and that's 2 seconds per cycle. And finally, the intersection with ID 2 is green for 1 incoming street only, and that's the Moscow one, and that's 1 second per cycle. Honestly, this output file confuses me. I don't know if I'm going to understand it better ever. Let's look at how it's scored. A score is awarded for each car that finishes its path before the end of the simulation. For a car that finishes its path at time t, the awarded score is F, and additionally, D minus T, 1 point for each second left when the car finished the path. In other words, if a car finishes at time t, it scores F plus D minus T, or 0 points otherwise. The score for the solution is sum of all scores of all the cars. This one looks at the example again and says, for instance, in the example above, the first car in the 0th second, it crosses intersection 0 immediately as the traffic light is always green. Then at second 1, which is 1 second later, it goes through the Amsterdam street. However, the traffic light is red. As for intersection 1, the submission has set the duration of Athens light to be green for 2 seconds. In time equals 2, the car now crosses the intersection and continues to Moscow. In time equals 5 seconds, the car has reached the end of Moscow and there's a green light at the end of intersection 2, so it crosses it and continues to Rome. This first car would have reached the end of Rome at t equals 7, but this is past deadline, meaning that 0 points are assigned to this car. For the second car, at the beginning, it finds a green light at intersection 1 and continues to Moscow. Then 3 seconds in, it reaches Moscow. There's also a green light at intersection 2. No cars are waiting, so it immediately crosses the intersection and heads to Londres. When time is 4 seconds, the car reaches the end of Londres, which is its destination. So, the second car finishes before the deadline and gets a score of 1000 plus 6 minus 4, and that is 1002 points. It took us that long to go through the problem statement, and that's fine because understanding this means you can think of a solution. My team discussed all of this quite a few times. We drew the example file on a paper, we looked at the figures again, and finally started thinking of a solution. Okay, so now we understand what the question is, sort of, and we know the main point. The first thing, like I said last time, is to have your input and output sort of ready, and if you're using object-oriented programming, make sure your classes are ready. I used my other program's template. I didn't even change the name, but then I changed it while making this video. As you see, I have the read input and the write output here. I have these classes that I'm going to show you in a minute. First, let's look at the read input file. Also, don't forget that according to the structure, there is something called input file, which has all of the input files of the question in here, and we are reading each file through this path and the file name. Just like last time, we are reading the file, and if we look at this, we have a line of numbers here, so we are going to read the first line first, and then we have lists of other things later. We know that the numbers are separated by space. Now that we have this line here, the first line, we need to read each of them. But first, let's look at the class. This is my first line. The duration in seconds, the number of intersections, the number of streets, number of cars, and the bonus points before the end of time. Then we have two lists. One list is the list of the streets, the other is a list of car paths. Let's look at them. In the street class, we have intersection start street, meaning this street starts at this intersection and it ends at this intersection, so we are reading both of them. And then it's the street name and the time it takes to go from the beginning of the street to the end of the street, or time start end street. Very creative, thank you very much. The car path is how many streets are in this car path, number of streets, and then each of the street names in a list, and they're all string. We'll look at the output file later. So we are reading the first line, making sure if they're integer they are parsed. After that, we are looping through the streets and reading these, but don't forget to start from 1 because we already used up this 0th line, and we have this number of streets, so we are looping through these and reading the integers and the strings. Then, for the car path, I actually had an error here because you have to start right where it ends here. This is the count of all of the streets read plus 1, and making sure. This one, I'm not sure that I understand what I wrote here, but it says the count of those streets plus the number of cars plus 1. And what does that mean? It means it already tells me that there are 5 streets and 2 cars. So I'm adding those up and I'm telling you to stop after you get to that number. So I sort of understand what I'm doing. Good for me. If you see here, I am using skip because after reading this number, I want to read a list of those. So I'm skipping the first or the 0th one, and then I'm reading this list and adding it to my car paths, and finally the read is done. Let's look at the solution. After reading the input file, we have to set up schedule for these intersections. At first, I wasn't sure what to loop through because we have a list of streets and then we have a list of car paths, and we have 2 cars here. 5 streets here, so I looped through the cars and the output wasn't good. But the main thing that for your first solution, which is always brute force because it's the easiest that you can edit, is to look at the output file and say how this input file turned into the output file. So here it says how many intersections there are, but as you see, there are 3 lists. So it's definitely more than the 2 of the car paths. Looking at this output file, we can create our output class, which is, as seen, the number of intersections that have a schedule, because there are intersections that may not get a schedule. Then we have a list, which I've called intersection schedule. It has the intersection ID, the number of incoming streets, and then another list, and that list is called order and duration green light, and it has the street name and for how long that traffic is green. So these variables have intersections, streets, cars, and these are from the input file. Then what I've done is I wanted to see how many unique intersections there are. So as you see here, I've taken these end of street intersections distinctly and now I have a list of unique intersections. Looping through that, I'm checking if I'm using the intersection or not, or even if it's usable. Then I start from an intersection from my list, get all of the car paths, which is now we have 2, get all the streets that use the current intersection. As you see, I've said from the streets where current and intersection is the current intersection. For example, if we are using 0 as the current intersection, then we get this one only. You may ask why I'm not using this side but using the end. Because it's saying incoming streets. Streets that lead to this intersection. How do we know that? The first street was Londres, right? And it's an outgoing street for 2, but an incoming street for 0. So this side makes the street incoming, and this side makes it the outgoing street. So the number of incoming streets is the count of this list, because we said it should be the end street of this intersection. The ID, I already have it, is the current intersection. Then I'm looping through all of the streets that are incoming to that intersection. To check if that street is used or not, I'm checking if this street is used at the beginning or at the end of the car paths. For example, Londres here is at the beginning and here it's at the end. If it's not a beginning street, so the count is 0, and if all of the end streets count to all of the streets that already exist, then that intersection is not used. And if it's not used, then there is no schedule. Continue. Here you see a bunch of commented code. Now, for this street, assuming it's used, I'm giving it the street name here. Then, if it's the start of the path, as Londres was, it gets an extra second before the traffic is green. As you see here, I'm checking if in the car path, the first street is the current street, then start off with 1. If not, start with 0. As you see here, I tried setting for how long this intersection should be green to how long it takes to pass the street, but it was wrong, so I just set it to 1 so that I could just solve it. There was no reason behind it, honestly. And that's it. I'm adding this here, and then if the intersection is not null, then add it. And I just have a right line for myself here, and making sure all of the stuff is added to my output file object, and then we are writing the output file. The first one is a number of intersections that have schedule, and then looping through all of the intersections that have schedule, we are adding the intersection ID, new line, not a space, and then number of incoming streets, another new line. And then looping through the green lights, we are adding the street name, for how long, and then new line, and that's it. We write the output file. So I'm running the first file. See here? This is what it looks like. As you see, only the order is different. So after seeing this, I was confident and I ran all of the other files. Don't forget, when changing the file name, make sure you save it before running it. As you see, the fourth file is the biggest, so we'll have to wait for that one. This is my third attempt at recording this part. See? Okay. As you see, the score is the same, and this time they added some interesting things. For example, there's a visualization element where you can see how each intersection is green or red. It has some insights, for example, how many cars arrived before the deadline, how long it took them, and things like that. So this was my first attempt at solving it. So as I said, it took us an hour to read through the question, and then I think 20 to 25 minutes before the deadline, we uploaded our solutions and we got around 4 million. And then we tweaked some things and got 6.7 million. And we didn't have much time to optimize anymore. So the extended round is for that. Looking at these insights, I'd say these two are taking up the most of the points. Because here it says I got 80% of the cars to reach before the deadline. Here it's 98, that's amazing. 68, 56, and oh no, that's not good. Let's read what it says. The submission scored that many points, which is the sum of 82,000 bonus points for cars arriving before the deadline, 500 points each, and 248,000 points for early arrival times. 165 out of 1,000 cars arrived before the deadline, which is 17%. How do we optimize this? Does it have anything to do with the order? Because here my output started with this one instead of this one. From what I understand, the order here matters, but the order in the intersection shouldn't matter. I'm still going to try and see how they came up with this order. I actually have an idea. If I upload their output file, let's see if the visualization is different. I got 1 more points. So this is 0. Oh, okay. Yes, they are different. So many changes in mine, but not many here. So there is a reason to the order. Intersection 1, 0, and 2. But if I look at the streets, so the longest that it's green should be at the top, and the more streets that there are? Okay, let's see if that makes sense. I'm going to do it at the end. I'm not going to check for if the intersection is used or not for now. I'm adding a little thing to the output line to say how many intersections have been scheduled out of the overall number of unique intersections. Now I ordered those two, so I need to order the whole list as well by the number of streets. The order should be descending. Don't look at this. So that worked. I'm going to run the last two files to see if there's a difference. Let's upload them while it's running. The moment of truth. Let's try the other files. I need to fix this thing. It's embarrassing. I'm just going to remove this. Why? I know it's integers, but forgot to save it. Oh. Right. Cool! Look! While this is running, I'm going to upload the files that already have the outputs. I don't really expect much for these because they already had a good percentage, but let's see. Cool. E has gotten the most improved up until now. F is nowhere near where it should be, I guess. I'm going to think while this is running. I don't know if... Let's look at E and F again. Yeah, no, this didn't change whatsoever. Because I'm not letting some intersections have schedules. That's because of this part. Not used. Does it make sense to use all of the intersections? Wouldn't I get errors and latency for the other cars? My biggest problem now is that I've solved the example input and output, so I'll have to optimize in my head. The other files are too big for me to debug them. I'm saying an intersection is not used if the street that I'm currently in is not a beginning street or it's the end of street. I'm going to remove this and just see what happens after this is done. Or I could think more while this is loading. I get the beginning street part. Look, we are looping through the streets, right? So here Londres is here, and it's the incoming street for this intersection. Londres is also an end street for this path. So I'm saying is in all of the car paths and all the incoming streets, I'm lost. Here, if we're saying if it's not a begin street is again about the intersection, but the end is 3 Athens, Moscow, Londres. So if the first intersection 1, if we are looking at this one, the incoming one is Athens, and Athens is not a beginning nor an end. So the intersection is used, you know? Because if you know, I don't. Please explain it to me. Okay, so assuming we are looping through the streets, if we looked at Londres, which is the example here, it's a beginning street and it's an end street, and all the streets are 1, 2, 3, 4, 5. So this one is 1, and it's not. It will be used. If we looked at Amsterdam, Amsterdam is just used here and it's not a beginning nor an end. Rome is the same. Moscow, Athens. Athens here is a beginning here. It is the beginning of this path. Rome is an end. So if we are looking at Athens, it is a beginning of a path, so this is not 0. And incoming streets, is Athens an incoming street? Yes, for this one. But there are 2 incoming streets, Amsterdam and Athens, for here. So this is also not true. Alright, so here this one, all streets, means number of incoming streets for an intersection. So if we are looking at this intersection, there are 2 incoming streets, 1 outgoing street, and the car is here. So this is the beginning of the path, not here. So if we're looking at Amsterdam, it is an incoming street, but it's not the beginning of a path, and it's not an end street anywhere. So now that we're looking at Athens, it's a beginning of a path, and also there are 2 incomes. This is 2, but here it is none, 0. Why do these things need to be connected? Can't I check? This is every car path that exists. Can't I check for just the intersection instead of all of them, so that I can deem an intersection unusable? How do I know what intersection is used? So Londres uses... This is done. Cool. Did not expect to get more here. From now on, I'll do most of my testing with this one because it has the least amount of cars arriving before the deadline. One thing I'm going to do is just comment this out and see if it makes it worse or better. I'm guessing this is worse, because this makes it true instead of false. I mean, it says it's not used. So we need better conditions. What makes an intersection not usable? Let's say nothing. Let's say go through all of them. This is interesting. I'm guessing because I'm using all of them now, the time delay and traffic usage is different. Okay, that is quite improved. I set that for time because I didn't want to go through all of the intersections, but why not? Time is all we got now. So 100 years later, we are back, and the final one is E. So while this is running, I'm going to upload all of the other files again. All right. Whoa. That is quite unexpected. Look at that. B got such a big boost. As much as I'd like to see 8 million here, I am happy with the improvement, and it's surprising that I didn't have to not use some intersections. I thought it would add to the queue, and I'm happy that I used it on the competition day because it made my program much faster, and I got to optimize it today. So that's great. I'm cleaning this code and uploading it to my GitHub, so you are free if you want to look at it, optimize it, use it however you like it. You can share it with me on Twitter and tell me how your competition went. That's it for Google Hashcode this year. Hopefully I'll see you in my next video, and maybe next year for 2022's Hashcode. I'm really thankful for the feedback for my last video. I'm glad it was helpful in any way. The feedback has really motivated me to create more videos, so thank you. If you'd like to see anything else, let me know. And I need to have an outro, so suggest one for me.